Okay, so the next guy on our list here, this is, by the way, the second lecture for Chapter 6. The next guy on our list here is Heisenberg, and he comes up with this idea of, let's see if I can back up a slide. I think I might have gone one too far. I did. He comes with this idea that the position and the momentum of the electron can't be known at the same time. And he develops his equation, which there's a ton of math that goes into. And it's based on Planck's constant. So remember, that is a number that has an exponential value of 10 times 10 to the negative 34th power. So we're only talking about things that are very, 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 very small. Anything that we consider normal doesn't apply to this. So if we talk about electrons, of course, these are really small, we say that this value has to be greater, the product of these two has to be greater than 10 to the negative third, negative 34th. Relatively easy, no big deal. But again, electrons are very small, and what we're talking about here, these values are small. So if I start to pinpoint the position x of the electron and say, okay, I can tell you that this position is very precise. In other words, my certainty is very, 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 very small. To compensate for that, to make sure that I am true to this equation, that it's greater than 10 to the negative fourth, this value has to go up. So pretty much what this means, again, is as this number becomes smaller, the position, the uncertainty of the velocity, the momentum, has to go up, and just the opposite. If the velocity or the momentum of the particle is very, very exact, then the position must be unknown. So it's just obeying this mathematical relationship that allows us to have this understanding. So to kind of put in perspective, it would be saying, for things that we know pretty well, we could say that, say, a person. It says, I can tell you that person is within a radius of 100 miles. And it's like, well, where do they live? Well, typically they live like in this one house within that 100 miles. That doesn't help you. I mean, you have to be more exact. So roundabout thinking, that kind of works for me anyways. Okay. Schrodinger, if you have anyone who you want to blame for quantum numbers, it's him. He goes through all this mathematical development and determines what some of the predecessors put together in regards to Heisenberg and Einstein and Planck, kind of figuring out where electrons could be found within atoms. And it's based on density, electron density, and probabilities. So we'll take a look at some of these numbers here just to have them make sense. It says an orbital is described as a set of 3 quantum numbers. I think just cross that out. We're really talking about 4, but we'll base it off 3 for now. So your principal quantum number is strictly just the energy level that the electron is found, just the energy level. If the principal quantum number is 4, I'm on energy level number 4, and just count down off the periodic table, row 1, row 2, row 3, to row 4. That's my first quantum number. The second quantum number is telling me the sub-level that I'm on. So it's kind of like the shape. So as far as giving me some numbers to work with, say I'm on the second energy level, principal quantum number n is 2, then I have 2 options. So the L value up here is always going to be n minus 1, yeah, scratch it off, n minus 1 down to 0. So if it's 2, my options are 1 and or 0. Those are my options. Always goes down to 0. And then we can make some connections in this in just a little bit. Here they are. So before I said I was in the second energy level, and that gave me this and this. That means my options as far as the sub-levels are p orbitals and s orbitals. Those are the ones that are available. And this works all the way through. This, again, will work better when we're in class for lecture. Then the third quantum number, the magnetic quantum number, gives us the orientation. So if it's an S, there is no orientation. It's just spherical. It could be anywhere within that sphere. But if it's a p orbital, remember that that has 3 orientations. It's got that x, y, z thing going on. So we could say it's going across horizontally or vertically. And if this was 3D, we could say it's coming, out of the page in a Z fashion as well. So it has three arrangements that you can have on there. And you can always look at the L value from a negative to a positive. So again, let's say I'm on the second energy level. I have two options. So I have 0 and 1. So 1 and 0. Well, for 0, it's -0 to +0. It's just 0. And again, that was my S. But if it's -1, or excuse me, 1, I could be -1, I could be 0, and I could be +1. So these are the orientations, the three different shapes. So this is going to require some memorization on your part just to have it work or make sense for you on a test. So this is kind of putting it one step forward, putting all these pieces together, and you can kind of pause this and take a look at it. It's in your book as well, and try to have it start to make sense. One extra layer, and I think our book does put this in there, is each of these orbitals you multiply by 2 for the number of electrons that are available, and that'll help you kind of go one step beyond what we have here. So the number of electrons that are on a particular energy level. So just looking at the shapes again, the S is considered spherical, and we'll look at that a little more here. This is interesting, and probably something you may not have looked at before, is this is all again based on density. And when we're talking about an S, say I'm in the third energy level, that tells us that the probability of finding an electron is kind of in this region over here. It's like a bell-shaped curve. But it could also be, as a probability, in a much smaller amount over here or over here. So it's based on this wave nature. So again, electrons are particles, but we're giving them this wave nature. So that was going back to de Broglie. And we notice that we have these low spots, so it's probably not going to be found here or here, but it has to do again with the density. And these little pictures here try to convey that as well. For P, it's the same idea. This is where these shapes come from as far as the density in which we find electrons. So again, we have the shape, which is this dumbbell, this P sublevel, and it has three different orientations in which you could have. So these are all listed here. And then D's gets a little more complicated, where you have these 5 different potentials for orientation where electrons could be found. And then I don't think we even show the other ones. Okay. Energies of these orbitals. If we just have one electron, we can say if it's in energy level 1, that's the energy. Done. If it's the energy sublevel number 2, or energy level number 2, it doesn't matter. It's all the same. So S's, P's, D's, it doesn't matter. They're all the same. But when you start throwing a bunch of electrons out there, it starts to get really messy. And you probably had to memorize this last year. An easier way of putting this type of a diagram together is to strictly just go by the periodic table and read from left to right, row to row. So if you take out your periodic table and take a look and say, well, row 1, there's only one S. Row 2, there's only, well, it goes from 2S to 2P, and I'm done. And then 3S to 3P, no big deal. But reading in the 4th energy level, you start with 4S, but then it goes into the D block, and remember that's always one less, the value. So it's 3D and then 4P. So it's just writing them out, just kind of go with that. That's probably the easiest way of memorizing it. And this is how the energies of the electrons are filled in the periodic table, but this only goes so far. When we're losing electrons, which we'll talk about later, we don't necessarily follow these rules. This is how electrons are filled along with the protons in the atoms. And degenerate just means that they have the same energy. We defined that, I believe, back over here. So we said electrons in the same energy level have the same energy. It means they're degenerative. Same thing over here. Okay, this last quantum number, we said there was 4. Here's the last quantum number. And this just differentiates that for each of these orbitals, there's 2 electrons that are found, and they can't be identical to each other. So they have different spins, they have different energies, and this has been identified by putting it through a magnetic field and noticing that they behave differently. So each one of these has a different spin to it. So this is a good spot to take a break, and we'll come back for a third lecture after this one.